So we're gonna pick up where we left off last class, and we're gonna show an example of implementing a stepwise regression. And as a reminder, right, this is all sort of a way of doing model selection. In other words, trying to determine which variables to include in the model. Okay, so I'm going to load a couple of packages. And so the most relevant one right now is this ISLR. The other, the GLMnet package will be for a little bit later. So ISLR is actually based off, it's a package put together as a data repository for one of the textbooks that I have linked in Canvas as extra reading material. What does it stand for again? 1 second. It is, just want to make sure I get it right. Introduction to Statistical Learning, with applications in R. And actually a lot of the lecture, not everything, but a lot of the lecture material is drawn from the book. And so it's actually a quite sort of nice introductory book, and it doesn't get too much into the weeds in stats. So if anyone wants to sort of augment their learning, I would highly recommend this this book. All right. So from ISLR, we can grab a data set called credits. And so we can actually take a look at this. Okay. You can see here a bunch of the variables. Let's actually look at the structure of this data. So it's got 400 observations across 12 variables. We have income, which is numeric, and then we actually have a bunch of integer. So the credit limit, credit rating, number of credit cards, age, education. I believe this is years of education. And then a couple of factor variables, gender, whether or not they're a student, whether or not they're married, and ethnicity. And then lastly, the balance on the credit card. Okay, so we are going to write.
Really quickly, your screen is frozen for me again. Is that on
no.
or is it for other people as well?
It appears to be frozen on my iPad as well. I don't know why this is happening, so let's try this again. We'll stop sharing. Sorry for that. And thanks for the heads up. So it looks like it's just loading right now. One of these days it'll finish loading, hopefully. Or we can try a version of this lecture where you guys don't get to see anything. You just hear the sound of my melodic voice telling you about credit data sets. Okay. It's loaded on my iPad, so is everyone good? I see a thumbs up. Okay, great. All right, so where was I? I was just kind of finished walking through, looking at all of these variables. Okay, and so as a refresher, when we do the stepwise selection, I am, selecting variables to put into my regression, right? And so I'm gonna sort of, as an aside, I'm gonna keep a separate sort of list of all of the variables, which are just the names. Okay. And so what we're going to be, the model that we're going to be sort of investigating here is to see whether or not, all of these variables can be used essentially to predict your credit card balance. So based off of demographics and certain things about your finances, can we estimate what your average credit card balance is? And so in the credit names, if I just run this, it's going to give me all of the names here that we see. But in fact, there's going to be a couple things that I don't want to include. And that's going to be the balance, because that's going to be our Y variable. So when we add variables into the model, you don't want to include that. And then the other one is just this generic ID, which doesn't really describe anything. And so I'm going to omit that as well. And so the way that I do that is I'm going to say grab all the names, and then I'm going to filter it, and I say grab all the names that are included in this vector, so ID and balance, but I have this exclam at the beginning, which says not that. So it'll be, if I didn't have this exclamation, it would read true, false, 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 all the way, false, 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 and then true for balance. But then it gets reversed so that it says false, true, 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 all the way up to balance, which will be false. And then it's going to grab those entries that are true in the vector and return that. So if I run this, I will see the same as before, except now I no longer have ID and balance. Okay, so this is the kind of starting point for all the names that we're going to include in as the pool of possible variables to include in the step forward regression. So you may have seen this type of thing being done several times before. Where I go through a for loop and I sort of continually add into these objects here. And so these are my initial objects that are going to essentially hold on to the models and variables as I walk through the stepwise regression. So if you remember, if I have like x1, x2, x3, x4, you know, first I look at the first layer where I take only one variable at a time, and then I pick the best one out of that, and then I continue on and add on the second one. I hold on to those two and then add the third variable and then the fourth variable. And so we need some way of essentially holding that variable that I decided to select. And so that's as well as the model. And so that's what these objects are going to be doing as we walk through the for loop. Okay. And so what I'm going to do is I'm going to loop through the length of the credit name. So it's going to be, you know, for 1 through, you know, 7, 8, 9, 10. So for 1 to 10, I'm going to look, I'm going to create a variable called available names. And this is going to be this is going to be an object that contains the pool of available names that I can pick from. Okay, so what is the difference between the available names and the credit names? So at the beginning, we have all of the variables, all 10 of them, right? But that is only the pool, that only represents the pool of available variables in the very first step. Because when I move on to the second step after I've selected a variable, let's say hypothetically, the variable that gets chosen in the first step is rating. I can no longer have rating in the available pool because you can't choose it twice, right? And so you need to be able to exclude that. And so what's going to happen is as I step through the first step, let's say it's rating. Rating is going to get moved into my selected variables object, which we'll see in a second. And then what will happen is that the available names is going to say, okay, everything in credit names, right? Everything in here, but take out everything with this exclam, take out everything in the selected variables. So once it's chosen, my available names gets modified to represent the actual pool. Okay, and then I'm going to create a couple more variables that essentially will be holding holding certain sets of values, which we'll get to in a moment. And so don't worry about these 3 lines. I'll talk about what they do. Okay, and so okay, I see a question. If we wanted to pre-allocate memory for all models before the loop, is there a way to create a vector of empty models? So so yes, there is a way to do that. I'm pretty sure you can do that with vectors, but normally it's done with matrices. And so I would assume that you can do it with vectors because vectors is just like a subset of what a matrix can do. And so you can set, with a matrix, you can set the dimensions and then everything can be empty as a way of pre-allocating the memory. And that, like if you're an engineer and you've worked with MATLAB, you know, that type of thing, it can be really important for making sure that the operation essentially operates really efficiently, because if you don't pre-allocate the size of your vector or of the matrix, it like recreates the vector or matrix every time. In this case, in these types of cases, I generally have never had to worry about that issue. The way that pre-allocation in R happens is going to be slightly different. And then the other thing is that for regression based approaches, it's all about that only really comes into play when you are dealing with data sets that have like really enormously large number of variables, right? Where this type of issue comes up. And actually I've never dealt with something like that before where pre-allocation becomes important. So I'll just kind of like comment. I'll leave that as a comment, but I do know that you can do pre-allocation. Okay, so okay, there are two sets of for loops that we need for the stepwise regression models, right? One is looping through each layer, and so in this case, right, we have 10 variables. So the outer loop is looking at all look at all the models with one variable, then look at the models with two variables, then with three variables, and so on and so forth. And then the inside loop is, you know, for all of the models with one variable, like go through all the possibilities, right? So you can think of the outer loop as doing the 1 through 10, and then you can think of the inner loop as doing all the ones within the 1, within the 2, within the 3 variables. So now we're working with setting up the inside loop. And I think you can really kind of qualitatively see what's happening here, because in the for loop, the thing that we loop through is all of the credit names, whereas in the inside loop, you're only working with the available names. Okay, so let me write this out.
Sorry, could you explain again what the outer loop does?
Yeah, so the outer loop is going to essentially hold all of the models that you've run for it's going to hold the best model in each layer. So the outer loop is going to say run everything in the inner loop, and then it's going to pick the best model for, say, variable 1. So let's say that's rating, and then it's going to hold that, and then it's going to move to the next loop, and it's going to run the inside loop for everything for 2 variables. It's going to be rating and something else. And then let's say the other thing is limit. So then it's going to say, okay, hold the rating and the limit, or it's going to hold the model that's just rating, and then it's going to hold the model that's rating and limit, and then go on, so on and so forth through until you have all 10 models. The inside loop is just going to run, it's going to run the model where balance against income, balance against limit, balance against rating, balance against cards, and so on, until it finds out that balance on rating is the best one, and then it's going to save that into the outer loop. So this code is going to write all of my available names, or it's going to write whatever single available names is. It's going to add it onto all the previously selected variables. So that's how you create the add-on variable for the next model. So let's say, so just to write out this particular line. So let's say selected variables, let's say we're in the third loop, and it's the ones that it has selected so far are rating and limit. And now it's going to work through, the rest of the available names. And it has this collapse thing. So what this is actually going to do is it will start with income. So it'll say income plus rating plus limit. That'll be the first one in the inner loop. And then the second one in the inner loop will be cards plus rating plus limit. And then it'll be age plus rating plus limit, and so on and so forth. So that is what this variables.hold line is going to be creating. Oops. What is happening here? Hang on. Okay. My keys got stuck. Formula.hold, and then if this is a way that you can create the formula. So all it's going to do is create the formula that you would put into your linear model. And so, my example that I gave earlier, so income plus limit plus rating, in line 20, it's just going to turn this into this. There's a special way that it passes formulas. And so we have this function here so that the model knows that we are passing a formula to it as opposed to other types of objects or strings and characters that are part of like a data table or data frame. Okay, and so now we just run the regression of formula.hold. We're going to use the credit data sets. Okay, and then we're going to grab the R-squared. And so if you remember in the stepwise regression on the inside loop, when we're comparing the models of one layer, so if it's just like balance on income or balance on limit or balance on rating, we choose the best one for the inside based on the R-squared, right? Because the number of parameters is not changing. And so it's okay to use the R-squared in this case, or it's commonly, it's most common to use the R-squared here. And the way that we grab it is through this function. So summary, which gives all those all that data that we've seen before several times. If you do $r.squared, you're able to grab the R-squared value. Okay, and so what we're going to do now is we're going to look at that R-squared, and we have to compare it to all of the R-squareds within my inner loop. So I'm going to go ahead and do that. So the first thing that happens is it's going to run through my first variable. So it's going to look at income, and it's going to run the model, and it's going to fetch the R squared. And then it's going to compare the R squared that I got to the best R squared. And in the very first step, we define that as being 0. So it's always going to enter into here in the first time. And now we're going to rewrite the best R squared, and it's going to get replaced with that hold value. So this means it's no longer 0. It's just equal to the first calculated R squared value. And you can see what's going to happen now is that as I move through income to limit to rating to cards, I will only enter the if statement if the R squared is better for any of these single ones. So let's say my R squared for income is like 0.8. Let's say the R squared for limit is like 0.7. So when I equals 2, when it looks at limit, it's going to run the model. It's going to look at the R squared, and then it's going to compare it against the first one. And it's going to say, no, this R squared is not better, right? Because 0.7 is less than 0.8. And so do not enter the if statement. But let's say I get to rating and the R squared is 0.9. Then it will enter the if statement, and then it's going to say, okay, now the best R squared is going to be 0.9. So as you walk through the inner loop, it's only going to execute this function to essentially grab the best model. And so we're going to say the best name is that whatever variable that we're on. So let's say rating. So it's going to say now the best name is rating, and then the best model is model hold, and the last model hold that we have is the one for whatever is here. So rating in this case. And then let's say it goes through all the rest of them. It doesn't find that any of them are better. So then all of these are going to be representing the best R squared, the best name, and the best model for rating. Okay, and now all we have to do is update this so that the outer, so after I've run through my inner loop, I now have all of this information for the best model, and we're just going to update our selected variables so that it is best.name and all of the previously selected variables. So in this case, in the first layer, let's say best name is rating. Initially selected variables is empty, so selected variables is just going to be rating, and that's it. And then on the next iteration, let's say limit is the best one for after we've moved through the second inner loop, then, or the second outer loop, then it's going to say selected variables, which is rating, saved from before, plus the new best name, which is limit, and now it's going to be 2. And it's going to do this until all of them are filled out. And then the other thing that I want to save is the model. So it's just going to be like this, and it will hold on to that model. Okay, then we can print selected variables so we can see which one is the best as it moves through. Yeah, and that's pretty much it. And with this set of code, we are now able to do this step forward regression. And so hopefully, I understand, this code can definitely be a bit complex, but it's important that you understand, how this works, as well as, kind of how to execute this. And so, if you have any questions, definitely let me know. And, moving forward, take some time to make sure that you really understand this. And so what we're going to do now is I will go ahead and run this, and hopefully it works. Okay. Cool. So we can see what happened here as I move through my outer loop. It actually selects a variable, and then it prints it at the end of the loop. So we can actually see in each step which of these which variable is being selected. So it goes rating, then it goes rating and income, then it goes rating income students, rating income student limit, and so on and so forth, all the way from 1 to 10. And so now I have all of the quote unquote sort of best models in each layer as selected by my step forward regression. And I can go through the list of my models. So actually we can take a quick look at these. So this should be a list of 10 models, each representing the regression results for what you're seeing here. And so you can see exactly that happening. So right, here's the rating coefficients and intercept and so on and so forth as we grab all of these. So now the question is, now that we have the sort of best in each layer, how can I select the overall best model? And so if you remember from last lecture, we talked about a whole bunch of model criteria that we could use. So like the AIC, the BIC, the adjusted R squared. And so we can actually now apply that to each of these models to figure out which one's the best one. So there is a function called AIC, and if I just pass the model to it, it will calculate that. And so this will be the first model, and if I run this, you can see, all models. It will give you this kind of mysterious number. You can use one of the apply functions to loop through the entire list and apply the function to all of those entries. And so if I go ahead and do this, I can actually see the relative, the AIC of each individual model. And remember that the AIC criteria is based off of the smallest value. And so all I have to do is look through here, find the smallest one, which appears to be model 6, right, 4, 8, 17. And this is actually a really nice example of essentially that bias variance trade-off that's happening. You know, in that particular example, it's talking about the total error term. In this case, that's not what this is, but it's kind of a representation of that, a proxy for it. And you can see the AIC value itself starts really high, gets low to some point, and then starts going up again as the penalty value, right, which is based on the number of parameters, increases beyond the sort of benefit value from the maximum likelihood estimator. And we can do a similar type of thing for BIC. And I can run this. And in this case, so you'll see model 1 starts at 5508, going all the way down until model 5, it looks like, is the smallest value. And so in this case, the BIC would point to model 5. And so model 6 is very close in terms of that value. But this is kind of getting to, the point that I was talking about earlier, or in last lecture, about different model criteria can actually, point to different final model selection. And there isn't necessarily a totally correct answer. It depends on how you are trying to sort of evaluate what is best. So there's still some bit of subjectivity in here. So the last one we can look at is the R squared, which I calculate manually. So we'll look at the summary of the object, and you can grab it with adjusted R squared. Similar to how we grabbed the R squared value in that for loop from earlier up here. So you do a summary of the model, $adjusted R squared. Okay, and so here we can take a look. So it starts out quite low, starts getting better and better. So in this case, we want the highest R squared value. So that looks like 95399, which is going to be higher than it looks like all of these guys. So in this case, the adjusted R squared value agrees with the AIC, and it says model 6 is the best.
Alan, I have two very basic questions.
Yep.
First of all, in line 34, what does this double square bracket mean?
Yeah. So that's an atomic vector. So when you work with lists, we are familiar with object and then square bracket like this as a reference for what's inside. The way that lists operate is the reference is with 2 square brackets. So that's just a particular thing about how they deal with list operators in R. And so when I grab the first model, it's with a double square bracket.
That makes sense. Thank you. Mm-hmm. And could you explain a bit what lapply does?
Yeah. So let's do this. lapply. So fake list. We're going to make a list with this. Oops. Okay. I just made a fake list with 3 objects in the list, and you can actually see, right, the double square bracket that I was talking about earlier. So the first object in this list is a vector of 3 numbers, 1, 2, 3, 2, 3, 4, 7, 8, 9, 10. So let's say I wanted to get the sum of each of the objects in the list. I can do this, sum fake.list1, sum fake.list2, and sum fake.list3. And if I execute these one at a time, it should be 1 + 2 + 3, which is 6. And then the next one, 2 plus 3 plus 4, which is 9. And then the last one, 7 plus 8 plus 9 plus 10 should be 34. Okay. So I can operate some kind of function on objects contained in the list. But you can imagine, let's say I had a list of 10,000 objects or 10,000 like vectors of numbers. I would not want to write these out individually. So I can do this nifty little function called lapply. And there's 2 entries for this function. One is the list that I'm operating on here. And then the second one is the function that I want to run across all of the objects within the list. So if I lapply the sum, it's going to return a list with the output of the function that I told to run it on. So in this case, hopefully you can see that I've asked it to essentially do the sum function of each object, and then that's what it returns. And so when we go up here, this has all of the models, and if I ask for the AIC of any particular model, it returns the AIC, and then if I do the lapply, it will calculate the AIC for every model in the list. Okay, so hopefully that clarifies that. Any other questions?
Hi, yeah, I have a question.
Yep.
So to choose between which the model that is the best, the only thing that we have to do is to choose the one with the highest or the lowest criteria, R-square or AIC. But my question is there any statistical test to identify if at least 2 models are similar or something like that? So, the difference between one and the other is not so much to think that one is better than the other?
Yeah. So again, it depends on your definition of better or worse. In this particular case, our criteria is basically the value of the AIC, BIC, and adjusted R-squared. And it's kind of hard to say, if the AIC values are really close, that then you could say, okay, these 2 models may be pretty similar. And that's because the relative differences are really context dependent on the model and the data. There are other ways that you can measure this. So if we go back to the cross-validation example, if you do like if I take these models that are identified through this initial one, and then instead of doing the AIC, BIC, or adjusted R-squared, I looked at the out-of-sample mean squared error, you could run that a whole bunch of times, and you could actually find slightly, like just based off of the out-of-sample randomness, that like, let's say model 6 has a lower out-of-sample mean squared error sometimes, but then model 5 would have a lower out-of-sample mean squared error some proportion of the time. And so you could run this a bunch of times, and then you could say statistically, like I could compare model 6 to model 7, 8, 9, 10 and say 100% of the time, it always has a better out-of-sample mean squared error. But then let's say it has only better than model 5, like 65% of the time. So that would be a way of, saying probabilistically based off of the sampling that you're doing, how close models are to each other. Yeah, and so that I would say is kind of like a robust test that you could do to say that. When you are, okay, so like backing up and thinking a little bit more sort of like philosophically about this, like when we're doing this, it's really about trying to find some kind of subset of variables. And so like if I looked at my adjusted R squareds, these are all, 0.953, something. And so you could say that like, okay, like any model, 5, 6, 7, 8, 9, 10 is probably going to be pretty close, especially relative to the difference in level to some of these other ones, right? You could even say even models 5, 4, 3, right? And you could probably say a similar type of thing where you could argue about the sort of relative magnitude of the differences in certain models compared to other models. So like the difference between 5, 4, 5, 6, 7 compared to any of those and 1, right? These are off by a value of like 1, whereas these are off by a value of a couple hundred. So statistically, there isn't necessarily a direct thing to say about just from the values, but you could probably get away with just arguing that the values are close enough that it's not really making a big difference.
Yeah, thank you.
Yep. Okay. I see another question in the chat about alternative ways to do stepwise regression using the step function. Yeah, so this is actually exactly what I was going to talk about right now. So stepwise regression is not like some really obscure like method that nobody except me teaches, right? Like I'm sure some of you guys have heard of this before. So then you might be wondering, well, why didn't someone build a function to do this already? And the answer is there is. And so it's has been pointing out in the chat, and I'll actually show an example of a different one right now that you could do. So let me just type this out. So this is one example of a existing built-in function where it just does both step forward and step backwards for AIC, and then one that does it for the BIC. It looks similar because you're just redefining the penalty parameter here. And you can run these. Oh, could not find function step AIC. Why is that? Did I load all of these? Okay, hang on. I might have forgotten to load a package. Yes, okay, this is in the mass. once again. Okay. Yeah, so this will run through everything, and it's going to give you the AIC and BIC values, and then you can go and essentially do the same thing. Okay. So there's certainly built-in packages to do this. My kind of principle for doing a lot of this stuff is kind of really making sure that everybody understands, and so that a lot of the operations are not like black boxes, which is why we spent so much time kind of walking through this as a way, hopefully, to reinforce the concept that we learned about in the last lecture. And so in the future, you know, there will be times where I may ask, so like I think on the homework, you'll be asked to at some point, you know, try and produce a similar version to this. And then other times, you know, you can just deploy the built-in functions. Okay, so let's take a quick break here. Let's say till 3:07. And then if anyone has any questions in the meantime.
Alan, can I ask a question?
Yep.
Move back to the function above.
Yep.
Yeah, that one, line 21, formula and the last step equals to blank space there. Is it like formula balance and then don't you need a plus there, or I don't know?
Yeah. Okay, so let me show you what's happening. Let's do this. Available.names. Let's say this is income. And then let's say selected.variables is rating. Okay, so I'm going to run this and we'll see what happens. So if available name is income and selected variables is rating, then we should have something that looks like this. Income plus rating. Okay. And then let me just copy and paste this part so you can see what's happening. It's going to paste balance and variables.hold and then separated by nothing. And I'll show you what the separated thing does in a second. So if I've now taken this and I've added balance to the front, and that's it. And so you can see that it retains the plus symbol that I had in the previous line up here. And the sep is just when you combine characters together, if you want to put anything in between. So if I do that, it'll put that in between the two things that I'm putting together.
Oh, what if you don't use the sep there? What happened?
Yeah, so the default is to put a space.
Oh,
so this will still work actually. If you do that, you can see now there's a space.
Wow.
And actually, since I've typed these notes, it's like been a couple years. I did learn, because I do this a lot. Where is it? Oops. So I do this. I used to do this a lot, where I just wanted to put things together without having anything separating. There's an alternative version called paste 0, which will do that, and then you don't have to put the default for this. Unlike paste, having a space is no space. So if I do that, the default is no space. So this is a little shortcut. Yeah.
Okay. And scroll down a bit. Yeah, and yeah, and the line 30, that selected variables, it's a, can I, let's say selected variables 2, so it's combination of best name and selected variables from the first one, or it should be selected variables?
Yeah, so you do have to be careful here. The reason why we're doing this is so that you can overwrite the previous one. So if you did this like that,
Yeah.
then the next time I walk through the loop, it's still gonna think my selected variables is nothing. And so it will not be able to walk through, it'll just print out the same thing every time.
All right. Yeah.
Yeah.
All right. Thank you.
Yep. Okay. So on that note, let's push on. And let's go to the whiteboard. Okay, so that's a more sort of classic method of model selection. Stepwise approaches. So more recently, there are more modern methods known as shrinkage methods or regularization methods. And so we're going to be talking about two of these today, the ridge regression and the lasso regression. Okay. So in our regular linear model, we want to, it's an optimization where we want to minimize the residual sum of squares. Okay, and so this is just sum I of yi minus yi hat squared, right? And the thing that the decision variables that we have are our betas. And so really what this ends up being is something like yi minus sum j beta j xij squared. And so what you're doing, right, is we are adjusting the slope of the line, in other words, the beta, so that whatever line that we end up choosing reduces the residual sum of squares as much as possible. Okay. And as I have pointed out before, you know, we can capture more and more of the variation by simply adding more and more variables, right? So you can imagine that if I add, so qualitatively, right, the way that I could think about this is, if I have more betas than x's, I will be sort of subtracting, or you will be, you can add more degrees of freedom to get closer and closer to your yi, which is what we were showing in that example with the x to the first power all the way to the x to the 50th power. And so some clever folks thought about a way of adding a penalty term to this equation. So we're going to minimize with an extra term. And it's going to look like this: lambda sum of j beta j squared. And so now my equation looks like this. So minimize the RSS plus lambda beta j squared. So this lambda is known as the tuning parameter. So let's look at this equation and kind of think about what it does. Okay, so this is we're going to think of this as the shrinkage penalty. At lambda equals 0, penalty has no effect. Okay, so when the lambda is equal to 0, then it is no different from an ordinary linear regression that we're used to dealing with, right? This whole term on the right-hand side, the shrinkage penalty, disappears. Okay, so what happens when lambda gets bigger and bigger? Let me actually make a new sheet here. So let me write out the full equation now. So now we have our residual sum of squares plus we have our penalty term. Okay.
Is there a residual sum square?
This term here is the RSS. Right, this is equal to y hat. So yi minus yi hat is your, oh, sorry, I see what you're saying. I need to square it.
Yeah.
Yeah. Okay, squared. Sorry, I misinterpreted your comment. Yes, indeed it is RSS, not RS. Okay, so conceptually, what happens is if my betas, if I just throw in more betas and they're really like big, this term is going to be increasing, right? And that's not what we want because we are trying to minimize this term. And so you now have this kind of balancing act. So the betas that have an important effect will try to stay close to the true value. Right, and so what's happening is you want this term to be subtracting from this term, and if you have the betas disappear, then you also have this driving up the value of your RSS, which you don't want. But in here, the betas that are not important will want to shrink. So this is a fairly sort of interesting model. Essentially what happens is that everything, and I should say, this is the example of ridge regression. So in the stepwise, we kind of introduce variables and then decide on which set of variables. When you do this kind of ridge regression or lasso regression, which we'll talk about in a second, you can introduce all of the variables all at once, and the betas will be calibrated in such a way that the model does the sort of best job as possible as according to this function, so that you may essentially get rid of some betas just by having this penalty term on the right, where it'll shrink away towards 0. So ridge regression can be difficult to interpret if K, in other words, the number of parameters, is large. And what happens is beta shrinks towards 0, but doesn't actually get to 0. And so the reason why we say it's a little bit difficult to interpret is because, let's say I threw in 1,000 variables, and it turns out that like 10 of those variables end up being really important, and it has these beta values that are going to look similar to the beta values that you would find if you just ran a linear regression with those 10 variables. The other 990 variables would have very small beta values, but they wouldn't actually be 0. But in that sense, you would still, in theory, kind of have to interpret them. And so this is one sort of extension beyond what we've been doing with the linear model, as a way of doing model selection, but in a sort of very different way, where you are not explicitly saying anything about the sort of quality of the variable, but that you can say something definitive about its effect on the explanatory variable. And so we'll look at this, at an application of this in a second. Let's see. And before we get to that, let's quickly cover the lasso regression. So this is essentially the same thing. So I'll just say RSS plus Now it's also got a penalty term, but the penalty term is slightly different. So instead of beta squared, it's the absolute value of beta. So absolute value, absolute, I know how to spell that. Absolute value instead of squaring. All right, so in this case, when lambda is large, betas can be forced to 0. And so in this case, oftentimes people consider this to be a little bit easier to interpret. Okay. How do we choose lambda? Does anyone have an idea about how you might go about doing this? I'll give you a hint. It is essentially the same kind of metric that we've been harping on over the last couple lectures now. Oops. So cross validation. The metric that we choose, the metric with which we decide on is the best model is based off of how well your final model does out-of-sample predictions. And so you can tune to 0, which is your kind of one end of the extreme, where you include the full effect of every variable. But when you do that, you run into the possibility of overfitting. And then you can start to increase the value of your lambda. So in such a way that the effect of certain variables will start to decrease, which will swing you in the other direction. You can think of as essentially decreasing the number of parameters, kind of, and getting away from this overfitting thing where you have too much variance in the model, variance contributing to the error term in the model. Okay. So let's jump over back to R. And 1 second. I can no longer, oh, never mind. So ridge and lasso regression. So we got the credit data set. We're gonna work with the same data set again. I'm just gonna go ahead and this time I'm gonna get rid of the ID column, which we don't need. And we can make the linear model. So this is a shortcut. So instead of having to write out all of the variables, you can just have this dot or period, which means run it against everything. And I'm also going to add a +0. And what the +0 will do is it says don't include an intercept term. We can run this, and we can look at the linear model, which includes all of the variables. And let's go ahead and run, or okay, we need to set up. This is just to kind of set up the inputs for the ridge regression, and it uses a function called glmnet, which I'll get to in just a second. So balance against everything using data credits. This -1 removes the column off the end, which is the balance column, which I don't want to include in my x's, but it's going to be in the y. So something like this, run both of these. And then we can run the ridge regression. Oops, glmnet. So GLM stands for a generalized linear model. We'll get more into detail about exactly kind of what that means a little bit later on in the class. But essentially what we're doing is we're kind of sort of modifying our original linear model in certain ways. And in this particular case, right, we're doing the ridge regression. So it is adding on this penalty term. And right now, what I'll do is I will set my lambda equal to 0, which means hopefully we should get a fairly similar result. Right, so the output is a little bit different. Let me see if I can grab these again. One moment. Yeah, it's just, I believe it's just beta. So if I do ridge $beta. Yeah, okay. So we can look at the betas here and they should be similar. I don't, I think in this case, the way that it actually solves is actually numeric now instead of an analytical solution. So you may see slightly different coefficient values. So if we take a look real quick, -7.8 for income, 18.77 for cards, -7.8, 17.72. So it is very slightly different because of the sort of estimation procedure. But generally, you're setting the lambda equal to 0 should have close, if not identical, values to just running the LM. So again, I'm actually going to this time copy and paste this, but we'll still kind of walk through this. This is, again, the k-fold cross-validation, which we will employ as a way of estimating the lambda. And this function is going to be identical to the k-fold function that I wrote in a previous lecture, except now modified to specifically be used for this example. And again, I'm kind of explicitly writing out the steps. So right now we want to figure out what the best lambda is. So to pick the optimal lambda that gives the lowest testing or out of sample mean squared error, we select the value for lambda, we perform the cross validation, we obtain the average test mean squared error, repeat steps 1, 2, 3 across a range of lambdas, and then select the one that has the lowest test mean squared error. Okay, so k-fold cross validation. I need the data input, the number of folds that I want to do, the lambda value, and the alpha. And the alpha is just a way of being able to use a lasso. It uses a different value of alpha. So if you do alpha equals 0, it's going to do a ridge regression. If you do alpha equals 1, it will do a lasso regression. All right. So really quickly, kind of stepping through this. Hopefully this will be review for most of you, but you know, if not, definitely make sure to go through this and make sure you understand. We are going to sample 1 through 5, right? Assigning an index to the data, referring to which fold that you belong into. And then we're going to go through each of the folds. We're going to create a training set and a testing set. It's going to be done in the same way that I had set up my X's and Y's originally with this model.matrix and the balance variable, except this time we're going to be selecting your index. And then you just run the ridge model with whatever lambda that you're trying to test out. We're going to do a prediction from the model, but using new data as the input. So this is how we test against the out of sample data, calculate the mean squared error, and then pass it out to hold the mean squared error. And then, yeah, ultimately, you're going to run the sort of full model and look at the MSE in comparison. So let's go ahead, set all of that up, and now that we have that function set up, we can think about what values for lambda to put in. So I'm going to create an empty object, an empty data table, and I'm going to loop through the lambdas that I want to test out. Okay, so the range of values for lambda can definitely be pretty tricky, and what lambda can take on a pretty sort of wide range of values. Wide in the sense that you're not doing lambda equals, 1, 2, 3, 4. You should be doing it by orders of magnitude. So lambda equals 0.01, lambda equals 0.1, lambda equals 1, 10, 100. And so that's what we're going to do. We're going to look at 10 to the sequence of -1 to 2 by 1. So these are the values of lambda that we're going to look at. We're going to sequence from 0.1 all the way up to 100. So we're working with an exponentiated value here. And so the name of my function is kfold.cv. We're going to put in credit as the input. We're going to have, let's just say 10 folds. Our lambda is going to be L, which is what we're passing in. And then the alpha is just going to be, oops, sorry, Ridge, not Lasso. And then alpha should be equal to 0. And we're just going to hold all of the models. So let me run this. Okay, took a couple seconds to run. And now what I would like to do is to, let's plot our out of sample mean squared error against the lambda value. So see what happens as we change lambda and what it does to the model's ability to predict. So we'll plot x equals log of the lambdas against the out of sample mean squared errors. So our x label is log lambda, and our y label is average test mean squared error. And let's just make a line of this as well. Okay, so run this. All right, and so what you can see here is that it's kind of doing this thing, although you know, the range that we chose maybe isn't necessarily the best, but as the value of lambda increases a lot, in other words, the penalty term, you know, it's going to shrink the betas more and more, and our our initial model is going to do very poorly out of sample. So let me see. So this plot that I'm putting here is, so this, I'll make a note of this. So this plots the lambda value against the out of sample or test mean squared error. And then if we want to look at what happens to the coefficients across lambda, we can plot that as well, which I'm doing here. So this plots the value of the coefficients against lambda. So what happens to our coefficients as we change our tuning parameter to get bigger and bigger? Okay, so in this case, what you can see is that everything kind of converges towards 0. It just so happens that we have some like numeric variables and some factor variables, and so the scale of it can be a little bit different. If I zoomed in just kind of on this part here, you will see the variables or the values start to shrink towards zero, especially the ones that are kind of the least important, as opposed to values that stay fairly straight and don't converge. So you can kind of see it's a little harder to see here, but the number of credit cards that you have and whether or not you're married, those look like they haven't started to converge towards zero again, which means that those are probably some, pretty fairly important variables. So that's kind of one way of qualitatively being able to assess what's kind of happening in this model in terms of, what variables are shrinking as you change the lambda. And if you kind of grab the lambda, our quote unquote sort of best lambda value, we end up with something like this with a lambda value of about 5. And you can run that and you can compare this against, let's take a look. In our stepwise regression, one of the things I think was like 4 or 5 variables. We can take a look at, how do those variables compare in terms of what happened to the coefficient. So if I do ridge $beta and I compare that to summary linear, and let's just do this. We can see that kind of one of the best traditional linear models, it's kind of close, right? 422, 417, 2.2, 1.8, 0.12, 0.14. And so on. And so you can actually see how the ridge regression is kind of getting close to the linear model, even though it's got all these other parameters in it. The betas for a lot of those have shrunk away, so that the values are, kind of fairly close to zero or kind of not really doing anything. And so that is the idea here behind the ridge and lasso regressions, is it's creating different coefficient values based off of this penalty parameter. Okay, let me. We can do the same thing for the ridge model as the lasso, as I mentioned before. Let's just change this to lasso. And we can leave the same lambda range. But in this case, the alpha will be 1 for lasso. We'll change this. And I can, again, sort of make a plot in the same way. So let's take a quick look. So as this runs. So similar type of plot here. And if you extend the lambda range, ostensibly this might get a little bit higher at the beginning, but sometimes it may not necessarily. It depends on the data set. And likewise, we can see what happens to the coefficients. Oops, I missed one line. Okay, and what you will notice here is that unlike the ridge regression, the values will actually go directly to 0 instead of converging to 0. And so at a certain point, all the variables will kind of wash out. And you can see the last ones to get to 0 are kind of the ones that the model thinks are like the most important. And I think we can kind of reflect that again as what we were saying before. I think that's the number of credit cards and then and your income, it looks like. But again, do remember that the scale of this matters. And so, and whether you're a student, the scale of it matters. So you do have to kind of zoom in to look at, you know, when the lines actually get to 0. It can be harder to tell if they're already close to 0. Okay. Oh, yes, you have a question?
Yeah, I actually have two questions.
Yep.
The first one, and maybe you said this already and I missed it, but can Lambda is restricted to being between 0 and 1, is that correct? Or it's
No, it is not. It is 0 to infinity. Yeah.
Okay, that makes sense. And then my second question is more conceptual. So how do you choose between, how do you know if you would prefer to do ridge or lasso, or I think there's a method that's a combination. I think it's called elastic net. How would you choose between?
Yeah, they are going to be fairly similar in the answer that they'll be telling you. Like different applications, you know, people have preferences for ridge versus lasso. My sort of general rule of thumb is like the lasso regression tends to be kind of nicer for interpretation when you have lots of variables because of the way that it actually converges to 0, so that you can more easily say which ones are kind of contributing, because you could have like thousands of variables or hundreds or even thousands of variables in the ridge where you're going to have tons and tons of values, and it can be harder to say whether or not they're contributing and the coefficient is just small, or whether they've been washed away by the penalty term. So there isn't, yeah, I don't think I can give you like a super clear answer on when to use one versus the other, like empirically. It's just like some people prefer one over the other. Okay, and then so you can see sort of the best lasso value was this one selected from our cross-validation procedure, and I can look at I can look at lasso $beta, and you'll see a lot of these variables are going to be similar in magnitude for the important ones. And then for a lot of the other ones, they'll be a lot smaller. Okay, and so you might be asking yourself again, hey, do we have to write a custom k-fold cross-validation thing? Is this like an obscure method that only Alan uses? No, that's not the case. This is kind of, again, a point of reference for you, just so that you can really internalize what's going on, and that if you ever did need to do some kind of custom version, you'd be able to write it yourself. But in fact, of course, people have made your life much easier, and so there's a built-in version of doing the cross-validation where it's CV, standing for cross-validation, .glmnet. And here you don't specify the Lambda because they're going to figure it out for you using cross-validation. So let's go ahead and run this. It's also a lot faster because whatever code that they're doing is probably way more efficient than whatever thing that I hacked together. But essentially, it's going to be doing a very similar procedure. It may not be exactly like a k-fold cross-validation procedure, but it is some kind of testing against an out-of-sample. And so we can get at similar types of plots. If you plot this, it's going to give you, you can see the log of your Lambda. So this is the value of the tuning parameter versus your mean squared error. And in this case, it's going to choose a very small tuning parameter. We can also look at what I was showing before. These are the value of your coefficients. So this one was that student one. I don't remember what all of these were, right? But this is the same kind of graph, and they kind of produce it internally automatically as well. So you can see what happens to the value of coefficients as you change the value of your Lambda. And I can then run the ridge regression with the best Lambda value, which you can call, so lambda.min. So this is the Lambda that minimizes the cross-validation procedure for your out-of-sample mean squared error. And ridge auto will then be your sort of best model. So if I look at the betas, this is the model that will provide sort of the best out-of-sample prediction. And this, of course, will work with the lasso as well. Where you have alpha set equal to 1, and we can look at how that changes some of these plots. For the mean squared error plot, I would hazard to guess, right? We've already looked at it. It should be pretty similar. You can see like this. And then we can look at the coefficients, and this one will be different. So you can see here, as opposed to converging to 0 and not really reaching it, the values in the lasso regression will drop to 0 after a certain point. And that's an artifact of how you solve for the absolute values in the penalty parameter. And then we can grab the best value of Lambda in the same way, lambda.min, and you can run that, and we can compare now actually the lasso regression against the ridge regression. So if I do lasso.auto $beta, you should be able to see they're not going to be the same. These values will be slightly different. Yeah, and so actually this kind of touches back on Sarah's question, if you really empirically wanted to demonstrate if the ridge or lasso is better, and it will depend on the circumstance, it will not always be the same, you could look at you could directly compare their predictive abilities. So you could look at the out of sample, the average of the out of sample mean squared error of my lasso model compared to my ridge model, and whichever one has a lower error, you could say is better, right? Yeah, okay. And so I think this is a good stopping point for us. So that kind of just about covers a sort of high level overview of the model selection methods, right? So we covered the criteria with which we evaluate them, AIC, BIC, adjusted R squared, and out of sample mean squared error. And then we covered the classical techniques, the most common classical technique through stepwise regression. And then now we've looked at some more sort of modern based techniques. These are especially kind of prevalent in the machine learning field for regularization and shrinkage using ridge and lasso regression. You can imagine actually the big benefit of doing some of these more modern shrinkage and regularization methods, right? And why this type of approach came to fruition in machine learning fields, because oftentimes they are dealing with data sets that have just a huge number of variables. And so, like in genetics, you could have data sets, that are based off of like sequences in DNA, and so the number of possible explanatory variables could be in the like millions, right? And so when I try to apply like a stepwise regression to that, I now have to do my outer loop, inner loop type of thing to millions of variables. And even though we reduce the combinations in our search from 2 to the n down to more sort of directly to n, it's still like oftentimes can be too big in certain types of applications. And so the nice thing about the ridge and lasso is that it's all done in the framework of this sort of single objective function, right? Single optimization problem, where I can simultaneously be able to kind of solve for all of the betas. And so that's not to say it doesn't get sort of computationally complex, right? But it is more often than not way more efficient than doing a stepwise approach. So yeah, there you have it. Yeah, so let's end here for today, and then I'll stick around a couple minutes for any questions lingering.